Welcome to the series of e-learning modules on practicals. Here we find the probabilities of more than one event which are dependent on each other using conditional probability and Bayes theorem. By the end of this session, you will be able to explain how to compute probabilities when there are two or more events which are not independent, which means conditional probability. You will also be able to explain the usage of Bayes theorem in conditional probability. Let's take a problem. In an examination, 30% of the students have failed in mathematics. 20% of the students have failed in chemistry, and 10% have failed in both mathematics and chemistry. A student is selected at random. What is the probability that the student has failed in mathematics if it is known that he has failed in chemistry? Let A denote the selected students who have failed in mathematics and B denote the selected students who have failed in chemistry. We have been given P of A is equal to 30% is equal to 0.3. P of B is equal to 20% is equal to 0.2. And P of A intersection B is equal to 10% is equal to 0.1. Probability that the student has failed in mathematics if he has failed in chemistry is P of A, given B is equal to P of A intersection B divided by P of B is equal to 0.1 by 0.2 is equal to half. Let's take another example. A box has 5 white and 2 red balls. Another box has 3 white and 4 red balls. One ball is randomly selected from the first box and it is transferred to the second box. After that, one ball is randomly drawn from the second box. Find the probability that it is red. Let event A denote the transferred ball is white, and let B denote that the transferred ball is red, and E denotes the ball drawn from the second box is red. Then probability of A is equal to 5 by 7. Probability of B is equal to 2 by 7. If one white ball is transferred to the second box, then there will be 4 white and 4 red balls. Then P of E, given A is equal to 4 by 8. If one red ball is transferred to the second box, then there will be 3 white and 5 red balls. Therefore, P of E given B is equal to 5 by 8. Event E can occur along with A and B. Therefore, probability that the ball from selected box is red is equal to probability of A intersection E union B intersection E is equal to probability of A intersection E plus B intersection E, which is equal to P of A into P of E given A plus P of B into P of E given B is equal to 5 by 7 into 4 by 8 plus 2 by 7 into 5 by 8, which is equal to 15 by 28, which is equal to 0.5357. Let's take another problem. A dice is thrown. If it shows even numbers, 2 balls will be drawn from box A. Otherwise, 2 balls will be drawn from box B. Box A contains 4 black, 6 white and 2 blue balls, while box B contains 2 black, 4 white and 2 blue balls. Find the probability that both the balls drawn are white. Let A denote box A is selected, B denotes box B is selected, and E denote 2 white balls are selected. Box A is selected if the number on the die is even. In a die, chance of getting even number is half. Hence, probability of A is equal to half. Similarly, probability of B is equal to half. After selecting the box, 2 balls are drawn from the selected urn. Hence, probability to E given A is equal to 6C2 divided by 12C2, which is equal to 5 by 22. And probability of E given B is equal to 4C2 divided by 8C2, which is equal to 3 by 14. Therefore, probability that 2 white balls are drawn is equal to probability of A intersection E union B intersection E, which is equal to probability of A intersection E plus B intersection E, which is equal to P of A into P of E given A plus P of B into P of E given B, is equal to half into 5 by 22 plus half into 3 by 14, which is equal to 17 by 77, which is equal to 0.2208. Let's take another problem. Plant 1 of XYZ manufacturing organization employs 5 production and 3 maintenance foremen. Another plant 2 of the same organization employs 4 production and 5 maintenance foremen. From any one of these plants, a single selection of 2 foremen is made. Find the probability that one of them would be production and the other a maintenance foreman. Let A denote plant 1 is selected and B denote plant 2 is selected, and A denote in a selection of 2 persons, one is a production and the other is a maintenance foreman. Since there are 2 plants, the selection of each being equally likely, we have probability of A is equal to half and probability of B is also equal to half. Probability of selecting 1 production and 1 maintenance foreman in a selection of 2 foremen. From the first plant, we get P of E given A is equal to 5C1 into 3C1 divided by 8C2, which is equal to 15 by 28. Similarly, P of E given B is equal to 4C1 into 5C1 divided by 9C2, which is equal to 5 by 9. The required event of selecting 1 production and 1 maintenance foreman in a selection of 2 persons can materialize in the following ways. Probability of A intersection E union B intersection E is equal to probability of A intersection E plus probability of B intersection E, which is equal to P of A into P of E given A plus P of B into P of E given B. This is equal to half into 15 by 28 plus half into 5 by 9, which is equal to 275 by 504, which is equal to 0.5456. Let's take another problem. Suppose a product is produced in 3 factories X, Y, and Z. It is known that factory X produces thrice as many items as factory Y, and that factories Y and Z produce the same number of products. Assume that 3% of the items produced by each of the factories, X and Z, are defective, while 5% of those manufactured by Y are defective. All the items produced in the three factories are stocked, and an item of product is selected at random. What is the probability that this item is defective? Let the number of items produced by each of the factories Y and Z be n. Then the number of items produced by factory X is 3n. Let A, B, and C denote the events that the items are produced from factory X, Y, and Z respectively, and let E be the event of the item being defective. Then we have P of A is equal to 3n by 3n plus n is equal to 0.6. P of B is equal to n by 5n is equal to 0.2, and P of C is equal to n by 5n is equal to 0.2. Also, it is given that P of E given A is equal to P of E given C is equal to 0.03, and P of E given B is equal to 0.05. The probability that an item selected at random from the stock is defective is given by P of E is equal to P of A intersection E union B intersection E union C intersection E. Using addition theorem of probability, we get P of A intersection E plus P of B intersection E plus P of C intersection E, which is equal to P of A into P of E given A plus P of B into P of E given B plus P of C into P of E given C is equal to 0.6 into 0.03 plus 0.2 into 0.05 plus 0.2 into 0.03, which is equal to 0.034. Let's take another problem. A manufacturing firm produced pipes in two plants, 1 and 2, with daily production of 1,500 and 2,000 pipes respectively. The fraction of defective pipes produced by two plants are 0.006 and 0.008 respectively. If a pipe selected at random from the day's production is found to be defective, what is the probability that it has come from plant 1 and plant 2? Let E1 denotes that pipe is manufactured in plant 1 and E2 denotes that pipe is manufactured in plant 2, and E denotes the defective pipe drawn. Hence, probability of E1 is equal to 1,500 divided by 1,500 plus 2,000 is equal to 3 by 7. Probability of E2 is equal to 2,000 divided by 1,500 plus 2,000 is equal to 4 by 7. Further, it is given that P of E given E1 is equal to 0.006 and P of E given E2 is equal to 0.008. P of E1 intersection E and P of E2 intersection E are the joint probabilities that the items are produced by the first and second plant and are defective. Also, P of E1 intersection E is equal to P of E1 into P of E given E1 is equal to 0.006 into 3 by 7, which is equal to 0.018 by 7. P of E2 intersection E is equal to P of E2 into P of E, given E2 is equal to 0.008 into 4 by 7, which is equal to 0.032 by 7. Using Bayes' theorem, probability of defective has come from plant 1 is given by P of E1, given E is equal to P of E1 intersection E divided by P of E1 intersection E plus P of E2 intersection E is equal to 0.018 by 7 divided by 0.018 by 7 plus 0.032 by 7, which is equal to 0.36. Similarly, P of E2 given E is equal to P of E2 intersection E divided by P of E1 intersection E plus P of E2 intersection E is equal to 0.032 by 7 divided by 0.018 by 7 plus 0.032 by 7, which is equal to 0.64. Since P of E2 given E is greater than P of E1 given E, it is most probable that the defective pipe has been drawn from the output of the second plant. Let's look at another problem. The probabilities of X, Y, and Z becoming managers are 4 by 9, 2 by 9, and 1 by 3 respectively. The probabilities that the bonus scheme will be introduced if X, Y, and Z become managers are 3 by 10, half, and 4 by 5 respectively. What is the probability that the manager appointed was X when the bonus scheme was introduced? Let E1, E2, and E3 denote the events that X, Y, and Z become managers respectively, and E denote the event that bonus scheme is introduced. We have given P of E1 is equal to 4 by 9, P of E2 is equal to 2 by 9, and P of E3 is equal to 1 by 3. Probability that bonus scheme will be introduced given that X becomes the manager, P of E given E1 is equal to 3 by 10. Similarly, for manager Y and Z is given by P of E given E2 is equal to half, and P of E given E3 is equal to 4 by 5. The event E can materialize in the following mutually exclusive ways. 1. Mr. X becomes manager and bonus scheme is introduced, that is E1 intersection E. Second, Mr. Y becomes manager and bonus scheme is introduced, that is E2 intersection E. Third, Mr. Z becomes manager and bonus scheme is introduced, that is E3 intersection E. Therefore, P of E equal to P of E1 intersection E plus P of E2 intersection E plus P of E3 intersection E is equal to P of E1 into P of E given E1 plus P of E2 into P of E given E2 plus P of E3 into P of E given E3, which is equal to 4 by 9 into 3 by 10 plus 2 by 9 into half plus 1 by 3 into 4 by 5, which is equal to 23 by 45. Using Bayes' theorem, the probability that X becomes the manager and bonus scheme is introduced is P of E1 given E is equal to P of E1 into P of E given E1 divided by P of E is equal to 12 by 90 divided by 23 by 45 is equal to 6 by 23. An insurance company insured 2,000 scooter drivers, 4,000 car drivers, 6,000 truck drivers. The probability of an accident is 0.01, 0.03 and 0.15 respectively. One of the insured persons meets with an accident. What is the probability that he is a scooter driver? Let E1, E2 and E3 denote the events that the insured person is a scooter driver, a car driver and a truck driver respectively. And E denotes the event that an insured person meets with an accident. We are given the following probabilities. Altogether, we have 2,000 plus 4,000 plus 6,000, which is equal to 12,000 insured persons. Hence, P of E1 is equal to 2,000 by 12,000, which is equal to 1 by 6. P of E2 is equal to 4,000 by 12,000, which is equal to 1 by 3. And P of E3 is equal to 6,000 by 12,000, which is equal to half. Further, we have given P of E given E1 is equal to 0.01. P of E given E2 is equal to 0.03 and P of E given E3 is equal to 0.15. Using Bayes' theorem, the required probability that an insured person is a scooter driver, given that he meets an accident, is given by P of E1, given E is equal to P of E1 intersection E divided by P of E, where P of E is equal to P of E1 intersection E plus P of E2 intersection E plus P of E3 intersection E, which is equal to P of E1 into P of E given E1 plus P of E2 into P of E given E2 plus P of E3 into P of E given E3, which is equal to 1 by 6 into 0.01 plus 1 by 3 into 0.03 plus half into 0.15, which is equal to 13 by 150. Hence, P of E1 given E is equal to 1 by 6 into 0.01 divided by 13 by 150 is equal to 1 by 52. Let's take another problem. By examining the chest X-ray, probability that TB is detected when a person actually suffering is 0.99. The probability that the doctor diagnoses incorrectly that a person has TB on the basis of the X-ray is 0.001. In a certain city, 1 in 1,000 persons suffers from TB. A person is selected at random and is diagnosed to have TB. What is the chance that he actually has TB? Let E1 and E2 denote the events that a person suffers and does not suffer from TB respectively, and E the event that the doctor diagnoses correctly. We are given P of E1 is equal to 1 by 1,000 is equal to 0.001, so that P of E2 is equal to 1 minus 0.001, which is equal to 0.999. Also, P of E given E1 is equal to 0.99 and P of E given E2 is equal to 0.001. Using Bayes' theorem, the required probability that the person actually has TB is given by P of E1 given E is equal to P of E1 intersection E divided by P of E, where P of E is equal to P of E1 intersection E plus P of E2 intersection E, which is equal to P of E1 into P of E given E1 plus P of E2 into P of E given E2, which is equal to 0.001 into 0.99 plus 0.999 into 0.001, which is equal to 0.001989. Therefore, P of E1 given E is equal to 0.001 into 0.99 divided by 0.001989 is equal to 0.4977. Here's a summary of our learning in this session. How to compute probabilities when there are two or more events which are not independent, which means conditional probability. Using of Bayes theorem in conditional probability.